So, today we're going to tackle a really fascinating question from the world of physics, and it's all inspired by Chapter 7 of the book Newton and Reality. We're going to build what the authors call a kinetic bridge, and it's this pretty amazing, surprising connection between the classical world of Isaac Newton and, you guessed it, the relativistic universe of Albert Einstein. But let's just start with a huge question. What if I told you we could get to Einstein's relativity by starting almost entirely with Newton? I mean, could we actually derive one of the most famous formulas in all of physics without using the usual starting points, like the whole thing about the speed of light being constant? Well, the answer is, believe it or not, yes. And we're about to see exactly how. And that right there is our goal, to follow this alternative path. Now, what makes this whole approach so incredible, and this is what the source material really gets into, is what it doesn't use. The entire proof, the whole thing, is built without relying on Einstein's foundational postulates. So no assuming the speed of light is constant, and no using Lorentz transformations. We're literally building this bridge straight from the bedrock of classical mechanics. Okay, so to build our bridge, we've got to start by laying the foundation on one side. And that side is the familiar world of Sir Isaac Newton and good old classical physics. You probably remembered this one from high school physics, right? Kinetic energy equals 1/2 mass times velocity squared. It comes straight from Newton's F equals ma, and you know what? It works perfectly for pretty much everything in our daily lives. Cars, baseballs, you name it. But, and this is a big but, it's built on a critical assumption that an object's mass is always constant, that it never ever changes. The problem is, once you start getting up to some really extreme speeds, that assumption completely breaks down. So what happens when we start pushing that cosmic speed limit? Well, this is where our story takes a really sharp turn. We just need to introduce one single relativistic plot twist. And here it is. This is the plot twist. The one rule change that connects Newton to Einstein is all about how we think about mass. See, in the classical view, mass is just mass. It's constant. But in relativity, mass is variable. It actually increases as an object speeds up. And this has a massive consequence. When you push on something, the energy you're putting in doesn't just make it go faster. Now, some of that energy gets converted into increasing the object's mass. So our trusty old formula for work, it needs an update to account for this new reality. All right, so with this new rule in our back pocket, we are officially ready to start our mathematical journey. We're going to forge the full relativistic energy formula right from these first principles. So how do we get from this new idea of work to a final formula? Well, the first step is we've got to deal with that pesky variable mass. The source text shows us that the change in energy that's due to the changing mass is related to the speed of light squared. So, by substituting this relationship into our work equation, we can actually get rid of the variable m and express everything in terms of constants we know, like the rest mass, m naught, and the object's velocity. Yeah, it gives us a more complex-looking differential, but it's one we can actually solve. And now for the key step, integration. It's really the same idea as in classical physics, where we integrate force over distance to find the work done. We are essentially just adding up all the tiny, tiny bits of work needed to accelerate our object from a complete standstill all the way up to its final velocity, v. The equation looks a lot scarier, I'll admit, but the mathematical principle is exactly the same. And when we finally solve this integral, the result is just profound. And that, my friends, brings us to the big reveal. Let's take a look and dissect the incredible formula that just pops out of that integration. And here it is. This is what we get, the final relativistic formula for kinetic energy. Now, I know it looks a little complicated, but it's telling a pretty simple story. It's just the object's total energy minus its rest energy. That's the energy it has just by existing. So the kinetic energy is really just the extra energy of motion tacked on top. And that extra energy that goes into increasing its mass, it acts like an inertial penalty. The faster you go, the more massive you get, which makes it exponentially harder to accelerate any further. And this right here leads us straight to the most famous equation in all of science. If we just rearrange our kinetic energy formula a little bit, we find that total energy equals mc squared. We didn't start with this, we didn't assume it was true, we derived it directly from Newtonian principles plus that one new rule. We've just proven that mass itself is actually a form of incredibly condensed energy. But hold on, are we absolutely sure this new complex formula is correct? I mean, the ultimate test is to see if it can turn back into Newton's formula when it's supposed to, at low, everyday speeds. We need to prove the connection is real. So let's put it to the test. There's a mathematical technique called a binomial expansion. And when we apply it to our big formula for situations where the velocity v is super tiny compared to the speed of light c, well, all the really complex parts of the equation become so small, they practically vanish. And what emerges from the math? What are we left with? You guessed it, exactly 1/2 m0v squared. At low speeds, Einstein's relativity just perfectly and elegantly simplifies right back into Newton's classical world. This graph is the ultimate visual proof. I mean, it just says it all, doesn't it? The green line is Newton's formula, and the purple one is our new relativistic formula. Look at how they overlap perfectly at low speeds on the left. They're identical. But as the velocity cranks up, you can see the classical model just completely fails, while the relativistic formula shows exactly how the energy needed for acceleration just skyrockets towards infinity as you get closer and closer to the speed of light. So, the really crucial point here is this. We forged a solid, powerful link. We started in the world of classical mechanics, we introduced that one single concept of velocity-dependent mass, and then, through integration, we arrived at special relativity. This shows they aren't two opposing theories at all. They're just connected points on a single continuous mathematical spectrum. The authors of the source material really said it best themselves. This derivation of relativistic energy constitutes the third link in the chain of proofs leading from classical physics to special relativity by a simple and easily accessible alternative path. It just highlights the power and the elegance of seeing these two monumental theories not as separate, but as deeply, fundamentally connected. And that really leaves us with one final, fascinating question to chew on. If the framework that Newton laid down over 300 years ago already contained the seeds of Einstein's relativity, just waiting for one new rule to let them grow, what other profound connections might be lying dormant, hidden in the foundations of science, just waiting for us to find them?